let's talk about the quotient rule, which is going to tell us how to differentiate, of course, a quotient of two functions. The good thing about this is if you already know the product rule, you can do the quotient rule pretty quickly. So let me show you how to derive the formula, and then we'll do an example. So this is going to work out whenever you see a quotient or a fraction. It's like f of x divided by g of x. And you want to take its derivative. And sometimes you'll see me write it just like f over g, and then take the derivative, because it just looks nicer and it helps keep me from having to write those variables all the time. So how can I find a formula for doing this? Well, here's the trick. It's kind of clever. So you can notice that f is equal to f over g times g. And the short story is just use the product rule on that, and then you're done. And this equation is going to be true so long as the denominator g of x is not 0. And that has to be a standing assumption. You're only going to be able to take the derivative if this expression makes sense in the first place. So what's on the bottom can't be 0. So let's try to take the derivative of both sides. You're going to get f prime. And then you're going to get the derivative of this product. And so let's use the product rule on it. And the product rule says that this derivative is going to be the derivative of the first factor, it's f over g, times the second factor plus the first factor times the derivative of the second factor. And to explain what's going on here, well, we don't know what this is, right? But if we assume that it exists, if we assume that the quotient has a derivative that exists, then even though we don't know what it is, this formula still has to be true, because this is a product of two functions. So this derivative, whatever it is, has to be there times g plus f over g times g prime. And so how can I find a formula for the derivative of f over g? So what I'm going to do is just literally solve this equation for f over g prime. And so you really just do the algebra to solve it. So let's move f over g times g prime to the other side. I'm going to get f prime minus f over g times g prime, and that's going to be equal to f over g prime times g. And so keep reducing the algebra. So what I would do here is find a common denominator for the left-hand side. So that's going to give you f prime times g minus f times g prime divided by g. Do you see how I did that? The term that had f prime by itself, I multiplied by g over g. And then that let me find the common denominator and then just rewrite that expression, the f times g prime. And so this is now equal to f over g prime times g. And to finally get your answer, all you have to do is divide both sides by g. So let me do that. You divide both sides by g. This one vanishes into a cloud of mist. And here multiplying by g gives us g squared. So that's the formula for the quotient rule. And from now on, when you see a quotient of two functions, you can just use that rule however you want. And for instance, let's take, let's take something like e to the x over x squared. And let's find its derivative using the quotient rule. So now e to the x is my function f, x squared is my function g. So the derivative of e to the x, that's e to the x, times function g, that's x squared, subtracting function f, that's e to the x, times g prime, that's 2x, so 2x. And then you're dividing by function g squared. So that's x squared squared. That's x to the fourth. And if you want to clean up the algebra a little bit, do some cancellations, then be my guest. So what you'll do is you'll break this up into two terms. Then you'll cancel x squared with a factor of x squared on the bottom. You're going to end up with e to the x over x squared for that first one. For the second one, you can cancel one factor of x, giving you 2 times e to the x over x cubed. So that's completely the same. And this is a quick way now of showing you how do you find the derivative when you've got a quotient of two functions. That's the quotient rule.